Window awnings that double as radiant energy collectors. When we think about windows, we think about light, comfort, and protection. Awnings, traditionally, are designed to shade windows from direct sunlight, keeping homes cooler while adding style to the exterior. But what if these simple structures could be transformed into radiant energy collectors? Imagine awnings that not only block heat but capture it, store it, and convert it into usable power. This is the concept of radiant energy awnings, a blend of architecture, free energy principles, and practical design. Today, we will explore how to design and build window awnings that double as radiant energy collectors, how they work, and why they could become a new frontier for sustainable living. The dual purpose of awnings. Awnings have been used for centuries to provide shade and reduce heat gain through windows. By blocking direct sunlight in summer while allowing lower winter sun to enter, they improve comfort and reduce cooling costs. They also protect windows from rain and add architectural detail to homes. But awnings are more than just shade devices. Their surface area, constantly exposed to sunlight and radiant heat, represents untapped energy potential. Every awning is essentially a platform waiting to be harnessed for energy collection. Radiant energy basics. Radiant energy refers to energy carried by electromagnetic waves, including sunlight, infrared radiation, and ambient electromagnetic fields. Most people think of solar panels when they hear radiant energy, but collection does not have to be limited to photovoltaics. Radiant energy collectors can include thermal surfaces, materials that absorb heat and transfer it to fluids or storage. Electrostatic plates, surfaces that capture ambient charges from the environment. Resonant coils, coils tuned to frequencies that pick up radiant oscillations. By embedding one or more of these technologies into awnings, they can become hybrid devices that both shade and collect energy. The concept of radiant energy awnings. The idea is simple. Awnings serve their normal function, but also act as energy harvesters. Picture a metal awning lined with special coatings that absorb heat during the day. Pipes embedded within the awning circulate water, capturing that heat to warm the home or provide hot water. At the same time, coils beneath the surface resonate with ambient fields, converting subtle oscillations into electrical charge. This hybrid approach ensures that the awning does more than block energy. It captures and repurposes it. Every window becomes not only a source of comfort but also a small power station. Structural design of energy awnings. To design awnings that double as collectors, consider the following components: frame, strong, durable, and angled for optimal sun exposure. Materials such as aluminum or steel work well. Surface layer coated with dark, heat-absorbing paint or integrated with selective surfaces that maximize infrared absorption. Embedded coils. Copper windings placed under the surface to capture radiant oscillations. Fluid channels, small pipes that carry water or glycol to store thermal energy. Control hub, a junction box that regulates energy collection, storage, and output. This modular design ensures that each awning is both an architectural element and an energy system. Thermal collection system. The simplest form of radiant collection is heat. Sunlight hitting the awning surface is absorbed and transferred into circulating water pipes. This hot water can be directed into storage tanks, used for showers, heating, or even preheating water for appliances. Insulation on the underside ensures that most heat goes into the fluid rather than escaping. A small pump keeps circulation steady, but in some designs, thermosiphon effects allow fluid to move naturally without power. This thermal system alone transforms an awning into a valuable energy collector, reducing reliance on conventional heating systems. Magnetic and resonant coil integration. Beyond thermal energy, awnings can also harvest radiant fields. By embedding copper coils tuned to resonate with atmospheric frequencies, small currents are generated. These can be rectified and stored in capacitors or batteries. Though the output may seem modest at first, multiple awnings across a building create a network of collectors. Their combined effect can power LED lighting, charge devices, or run small fans. The key is resonance, tuning the coils to frequencies where natural oscillations are strongest. For advanced designs, permanent magnets can be integrated near the coils, amplifying oscillations through field interaction. This merges traditional free energy concepts with practical architecture. Hybrid energy output. The real power of radiant energy awnings lies in their hybrid nature. During the day, They capture solar heat and radiant fields simultaneously. At night, stored thermal energy continues to provide warmth, while resonant coils draw from ambient fields. This dual output ensures that the system is not dependent on one energy source. Even on cloudy days, coils continue to harvest, and even at night, thermal storage provides utility. The awnings become part of a self-sustaining loop, complementing other free energy experiments in the home. Practical benefits: radiant energy awnings offer several advantages: energy savings, reduce heating and electricity bills; sustainability, turn waste heat into usable energy; architecture integration, no need for separate panels or collectors cluttering space; scalability, add more awnings to increase capacity; independence, reduce reliance on external energy supplies. For those who value both aesthetics and experimentation, radiant awnings represent a perfect fusion. Safety and durability. Because awnings are exposed to the elements, durability is crucial. Surfaces must resist corrosion, coatings must withstand UV exposure, and coils must be sealed against moisture. Thermal channels should use antifreeze solutions in cold climates to prevent freezing. Safety also includes electrical management. Coils must be properly insulated, and circuits must include fuses to prevent overload. Energy collected should be routed through safe storage units rather than directly into appliances. With proper care, radiant awnings can last for decades, providing continuous energy alongside shade. Pause for a moment and imagine this: you stand inside your home on a hot summer day. Sunlight blazes outside, but your awnings keep the interior cool. At the same time, those same awnings are collecting heat for your water tank and capturing radiant oscillations that power your evening lights. Your home becomes a living example of free energy, where every ray of sunlight and every invisible wave is transformed into something useful. Would that not be one of the most elegant ways to prove that free energy is real and practical? Testing and experimentation. Building radiant awnings begins with prototypes. Start small: a single window awning with a thermal channel. Measure how much heat it captures and test how long it stays warm after sunset. Next, embed a simple coil beneath the surface. Use a multimeter to measure voltage during different times of day and weather conditions. Experiment with coil shapes, from flat spirals to cylindrical loops. Adjust capacitor values to tune resonance. Keep records of every test. Even if results seem minor, improvements accumulate. Over time, the awning becomes more efficient and effective. Applications beyond homes. The potential of radiant awnings goes beyond residential use. Commercial buildings with rows of windows could harvest enormous amounts of energy. Schools, offices, and hospitals could use radiant awnings to reduce costs and demonstrate sustainability. In rural or off-grid areas, radiant awnings could provide both cooling and essential energy collection. Disaster shelters could use them for lighting and hot water without fuel or grid dependence. Even greenhouses could integrate awnings to regulate temperature while collecting power. Challenges ahead. Like all experimental systems, radiant awnings face challenges. Thermal efficiency depends on insulation quality. Resonant coils may require precise tuning that changes with weather. Structural weight and wind resistance must be managed. Yet every challenge is also an opportunity. Better materials, smarter designs, and more creative arrangements will solve these issues. What seems experimental today may become standard architecture tomorrow. The vision of energy. Collecting architecture, radiant energy awnings represent a broader vision: buildings that are not just consumers of energy but producers. Every wall, roof, and window could harvest energy passively. Homes would no longer drain resources, they would generate them. The awning is just one example. It shows that small architectural details can be transformed into powerful tools when paired with free energy principles. From shade to storage, from style to sustainability, awnings prove that innovation does not always require radical change. It often begins with reimagining what we already have. Window awnings that double as radiant energy collectors are a practical, elegant, and inspiring way to merge free energy experimentation with everyday living. By combining thermal capture, magnetic resonance coils, and durable design, these awnings shade homes, reduce costs, and generate energy all at once. They may start as prototypes in workshops and backyards, but they represent a vision of the future. A future where every home is a power station, every surface is a collector, and every beam of sunlight is transformed into utility. The journey begins with one window, one awning, and one experiment. And from there, the possibilities are limitless.